Okay, so let's look at an example. How can we optimize an approximator that uses the sigmoid activation, for instance, a single neuron that uses a sigmoid activation. So we'll see this as an example, and later on we'll generalize this into a full network. So let's assume a single neuron with a sigmoid activation function, right? And so I provided here the sigmoid activation function and then the derivative of the sigmoid activation function. Z in this case will simply be the linear combination Wx plus B, because we'll take this linear combination and pass it through our activation function, our sigmoid activation function. But still we need to compute the gradients with respect to our tunable parameters, which are W's and B's. Right, so we need to compute the derivative of our loss function, and as before, let's just assume the squared error loss with respect to W and also with respect to our bias term. Okay, how can we do that? So as before, we'll use the chain rule. So instead of computing the derivative in the loss with respect to W's or B, we'll compute the derivative of the loss with respect to our activation function, g of z, and then we'll multiply that by the derivative of our activation with respect to the input, to the linear combination input, and then the derivative of the linear combination with respect to W or to the bias term. So let's assume as before that we are given a set of labeled observations, x and y, and now we want to perform a gradient descent step. So how we do it? We set the new W to be the old W minus some learning rate multiplied by the gradient in our loss function. This translates into the derivative of our loss function with respect to the activation, right? So it might translate into the TD error or the difference between our approximated value and the true value, the true y, multiplied by the gradient in our function approximator, in the activation function, in this case, in the sigmoid neuron. So let's write this out. So our approximation value following the sigmoid function is 1 over 1 plus e to the power of minus z, right? Z, as we said before, is our linear function, minus y, which is our label. And now we multiply that by the derivative of the sigmoid function given here. And finally, we multiply that by the derivative in our linear approximate. Right, so this is exactly what we have here. This portion is the derivative of the squared error loss. This portion in red is the derivative of the sigmoid function, and the blue is the derivative of our linear approximator. That can be either x if we would like to compute the derivative for w's, or it can be 1 if we're computing the derivative for the bias term. Okay, now we can connect several of these neurons with activation. So, going back to the same question we asked before, what if we connect several neurons to combine a network? So as before, x is the input, zi is the activation vector for layer I, wi is the weight matrix for layer I minus 1 to I, with dimensions zi minus 1 to zi. What is the output of layer 1? Well, the output of layer 1 is the linear combination of x and w1, but now when this is pushed through the activation function. It can be sigmoid, it can be something else, but as long as it's a non-linear activation function. What is the output of the network? Well, the output of the network, again, we have to pass each layer, the activation of each layer, through the activation function. And once we do that, we cannot do the trick that we did before. This does not collapse into a single linear approximator. More than that, it can actually represent any continuous function to arbitrary precision. As we said before, this is the universal function approximation theorem. In specific words, it means that given any continuous function f of x, if a two-layer neural network has enough hidden units, then there is a choice of weights that allow it to closely approximate f of x to approximate it to arbitrary precision. Right, and the same theorem also can be shown for a fixed width network with sufficient number of layers. And there are also other variants of the universal function approximation theorem, but they're not very relevant for this course at least. So let's see how we can define a neural network with NumPy, the NumPy library in Python. So we can do it as follows. It can actually be pretty simple. This is without training though, right? But just defining the neural network is very, very simple. So we can define the network as follows. We take as input the number of layers and size for each layer. We take a matrix, right? For each layer we have a vector of biases. And then we have a tensor field of weight matrices, one weight matrix per between every two layers. Okay, then we have to define the sigmoid activation function, and now we can define the forward path through the networks. That is, for each B vector, bias vector, and W matrix, we take the initial input, this is what we do initially, and pass it through the dot product between W and A, and we add the bias vector, and then we push everything through the sigmoid activation function and continue with this activation to the next layer until we finish going through all of our layers and we return the output. Okay, so just defining a deep neural network is as simple as that, right? It's just a set of matrix and vector multiplications to get the output. Of course, this doesn't tell you anything about how to tune these W's and B's. We'll see this in a second. Okay, we'll see this next.